All right, what are we doing today? So we spent the past few days talking about sets and functions and cardinality of sets, infinite sets. And today we are turning to an entirely new topic. So which is number theory, which I personally am excited for because number theory happens to be my own area of research. So the stuff that we're doing in this class will not exactly be what I'm working on, but it is, the basic stuff in the field that I work in. So I'm very happy to talk about it. And I hope that I can say some things that you will find interesting. So we will start today with some basic topics of divisibility and modular arithmetic. And with that, let's get started. So we'll start with what might be a familiar definition. So let's say we have two integers, a and b. With a different from 0. Then we say a divides b. A divides b, and write this a bar b. So this is a divides b, this notation. And what this means is there is another integer c such that b equals a times c. So another way of saying this is that b divided by a is an integer. Because of course, this is what c is. So hopefully this is familiar. Sometimes when you have two integers, then dividing one by the other will not result in an integer. For example, 1 is not divisible by 2 because 1/2 is not an integer. But for example, 12 over 2, you can also write as 6, so 12 is divisible by 2. Right, I guess let's write down some proper examples. Or maybe before that, let me say there's also this notation. So I guess I set this up there, but for concreteness, let me rewrite it here. So this means a divides b, and this, if you put a little slash through it, means a does not divide b. Okay, so that's our definition. So, for example, 3 divides 12, because 12 equals 3 times 4. So this is c in our definition. And as a non-example, 5 does not divide 12 because there is no thing that you can put there to make the equation work. Or in other words, 12 over 5, not an integer. Right. So I want to write down a couple important properties of divisibility. If a divides b and a divides c, then a divides b plus c. So this is just a little relationship between if b and c are both divisible by a certain thing, then b plus c is still divisible by that 3. And a couple more along these lines. If a divides b, then a divides b times c for any integer c. And one more. If a divides b, and b divides c, then a divides c. This is some kind of transitivity. Last one. And let me prove the first one for you quickly. The other two are quite similar, and I will leave them as exercises if you're interested. So proof of this first one. Well, let's start from the definitions. A divides b means b equals a times c for some c integer, and a divides c means b, oh, let me not use c because I am using that somewhere else. Let me call it s. And then a divides c as well, which means that c equals a times t, so t in z. And then if we add them together, b plus c, we can rewrite them using these expressions. So b is a times s, and c is a times t. And then we can factor out the a. So we get a times s plus t. And now if we look at this, what are we saying? B plus c equals a times something. And this is exactly the statement that b plus c is divisible by a. So a divides b plus c. And the other two are similar. Now, this has been fairly basic so far, but already there are some quite interesting things to say about divisibility, and in particular about these three important properties that it satisfies. But I'm going to limit that to a post on Piazza because I think it's outside the scope of this course. But those are the basic rules for now.